Gases are everywhere in the Earth's atmosphere, and in fact, basically all of it is made up of them. Their molecules come in different shapes and weights depending on the element that they are, and yet we barely notice them. However, just like everything else in nature, there are laws and guidelines that govern and control their behavior. The basic guidelines for all gases, no matter what conditions, are called the kinetic theory of gases. This theory states that all gas molecules move in a continual random motion and always in a straight line, bouncing off surfaces when they reach them. That the volume of the actual particles is so close to zero that it is negligible. Therefore, the volume of the gas is drawn from the space that it actually occupies. Also, the tiny intermolecular forces that hold the atoms together have a negligible effect on the particles as they zip around. Temperature is the average for how much kinetic energy the gas molecules have, regardless of what element they are. And finally, gas pressure is from the collisions of the particles against each other and the walls of the containers that they are in. From these basic guidelines, multiple gas laws have been drawn, each with their own variables that can apply to all gases depending on the conditions. These laws are Charles's law, Boyle's law, Avogadro's law, the combined gas law, the ideal gas law, Dalton's law, and Henry's law. All of them are applicable to all gases, no matter what type, as the depending factor is the conditions that that gas is in. Charles' law is one of the main laws that is applicable with liquid petroleum gases, or LPG for short, and the methods that they are used to mine, transport, and store them. Charles's law states that the volume and temperature of a gas at a constant pressure are directly proportional to each other. This means that as the temperature or volume rises, so does the volume or temperature of the same amount of gas. The inverse is also true, meaning as either condition drops, so does the other. These conditions are constantly achieved through LPG production. As for the mining of these gases to be commercially profitable as possible, they are transported and stored on the borderline of each gas's respective boiling point, making them a liquid for the duration. The gases that are mined via LPG facilities are mostly propane, butane, methane, and ethane. These are all hydrocarbons and are found commonly throughout the Earth's crust. The facilities that mine them take the raw gas from the deposits and separate each of them out in a distillation tower. The tower separates all the gases using different temperatures and pressures at various points up the column until the gases split out from the main flow. The now pure hydrocarbons are then run through 3 cooling stages until they finally liquefy, ready for storage and transport. The first stage is the simplest, running the fresh, high pressure and hot propane through 30 degrees Celsius seawater to cool it down to that temperature, from the 70 to 150 degrees that the deposits normally rest at. The now slightly cooler gas is run into the first refrigeration unit using already liquefied propane as a refrigerant. This cools it down to minus 20 degrees Celsius, while at the same time dropping the pressure slightly due to the lower temperature. The pressure drops slightly because of the individual molecules have less kinetic energy now and therefore move slower, bouncing off each other and the walls of the container less often. The now much cooler propane is run through another refrigeration unit of the same design, dropping the temperature until the gas reaches minus 42 degrees and condensates into a liquid. The liquid hydrocarbons are then stored into a giant sealed storage container at the atmospheric pressure, ready to be offloaded onto an LPG tanker for transport to land. This whole process is performed to make mining these hydrocarbons as commercially profitable as possible. As Charles' law states that the temperature and volume are directly proportional, it can be seen in the real world by the cooling of these gases. Propane specifically has an expansion rate of 600, meaning that the exact same amount of propane will take up 600 litres as a gas, but only 1 litre as a liquid. Therefore, LPG companies are able to cram a lot more of the hydrocarbons in at a time, making the profit of each shipload much more. But say you didn't know the expansion rate of one of the gases and wanted to figure out what the volume of it was at a specific temperature. To do this, the equation for Charles' law can be used to figure out whichever unknown you wish to find. The equation is V1 over T1 equals V2 over T2. The different variables in the equation are the initial volume and temperature and the final volume and temperature. However, this is just the base equation and can be rearranged to find any one of the 4 variables. Volume is always found in litres and temperature in Kelvin, meaning that you would have to convert it into those units if you had such values in a different form. One example that is used a lot in the LPG world is trying to find the final volume when all others are known. This would rearrange Charles' equation into V2 equals V1 over T1 times T2. Once it is rearranged, all you have to do is substitute the numbers in for each of the variables. For our example calculation, let's say that V1 equals 500 litres, T1 would equal 30 degrees Celsius, and that T2 equals minus 42 degrees Celsius. But remember, before we can even start, we need all the temperatures in Kelvin and all the volumes in litres. To convert Celsius into Kelvin, all that is needed to be done is to add 273 onto each temperature. This makes T1 actually equal 303 degrees Kelvin and T2 equal 231 degrees Kelvin. Now finally, we have all our values ready for the equation to substitute in. Do the math and we get an answer of 381.2 litres with rounding to 1 decimal place. These calculations are used a lot in the world of LPG to keep everything running smoothly and the people on board safe. The instruments they have on board monitoring the whole operation can sometimes be a bit out, so it is good to have the knowledge to actually figure it out yourself. After all, I know I'd rather not be blown up when some simple math could have saved me.